this time we will talk about Newtonian gravitational force, part 2 of the series. And in this video, we're going to solve a problem on finding the gravitational field due to a spherical shell. If you did not watch part 1 of this series, please go back and watch video 1, because in that video we did a setup for the notation that will be used for the rest of this series. You will find the link to that video down in the description. Just to remind you, in general, if you have 2 point masses, a very small size masses compared to the distance between them, then the Newtonian gravitational law says that the force, the attractive force of gravity between the two masses is equal in magnitude to a constant called the universal gravitational constants times the mass 1 times mass 2 and divided by the distance square. Remember, this expression in its original form is valid for small masses, small size masses. So now, our famous problem that you will find in many textbooks says the following: find the gravitational potential and gravitational field strength due to a spherical shell of radius r and uniform mass density, let's call it sigma, everywhere outside and inside the shell. Before we start the problem, just to remind you about these physical quantities that we are talking about. The gravitational potential, which we'll call V, capital V, is really, it's equal in form minus capital G, the mass that's producing this, that's creating this gravitational potential, divided by R, which is the location, the distance from the origin to the location of any point you are interested in. Now this resembles the electrostatic potential. The other quantity is called the gravitational field strength, G vector. It's a vector quantity. Remember that for the potential, the gravitational potential, it's a scalar. However, for the field strength, it's a vector. So G vector is minus G mass that's creating the field divided by R square, R unit vector. And the meaning of the minus R unit vector is for direction, to say that gravity is an attractive force, of course, so the gravitational field is toward the center where the mass is located. Of course, we have also the force between two masses and the potential energy between two masses, which are also written in red font letter. So, to solve this problem, we will use spherical coordinates. As I said before, you will find this problem in many textbooks, in many lectures, in few YouTube channels. However, I found that in many times this problem and other problems, they are solved in a specific method, not in the general way. For example, in this exercise, usually what many textbooks do is they will cut this shell into slices, horizontal, think of horizontal slices, so you're going to get rings. So you can think of this sphere as a stack of rings. And then once you know the gravitational potential of one ring, then you can add all the contributions together to get the total potential of the whole sphere. Now, personally, I don't like to use this method. I prefer to use the most general way of using vectors and spherical coordinates. I encourage students at the university level, in physics, in mathematics, in engineering, and whoever is interested in this type of problems, to use the most and to learn the most general skills that are needed to solve the problem. So we're going to be using some vectors and spherical coordinates. Just a few things from spherical coordinates. So let's look at the picture. We have a shell of radius capital R. Now here, in spherical coordinates, we have three coordinates that we are using. One is called r small. And in our example, really r small is nothing but the whole radius of the sphere because it's a shell. So there is no mass inside. The mass only exists on the surface of the shell. So in this case, small r is nothing but capital R, and that's the radius of the shell. So in vector notation, I'm writing here in the second line, r vector is equal to the magnitude, which is capital R, that's the radius of the shell, and the direction is r unit vector. The other parameter or coordinate that we use in spherical coordinates is the angle theta. Now if you look at the picture, theta is the angle between the z-axis, the positive z-axis, and r. So that's the angle theta. And the last coordinate we are using in spherical coordinates is the angle phi. Now this is an angle between the positive x-axis and the projection of r on the xy plane, the shadow of r on the xy plane. The angle between the positive x-axis and the shadow is called phi. Now it's clear that phi takes the values from the smallest value, which is 0, and it goes around 2 pi. That's a full rotation. While for theta, the smallest value will be 0, which means that you are on the positive z-axis, and the maximum will be pi, which means you are on the negative z-axis. So now, let's take a small piece of mass on this surface. So here I'm drawing a red piece on the surface of the sphere. Now the piece looks big, but really I just made it big just to be clear. However, think of it as a very tiny, small piece of the surface. So now, what is the mass of this small piece? Well, the mass is equal to the density, which is assumed to be constant, and we call this sigma, times the area of this small piece. So here in this line, the third line, you find that dm, that's the small mass of this piece, is equal to the density, that's sigma, times the small area of that piece. Now the small area of that piece in spherical coordinates is equal to the radius square, which is constant, that's capital R square, times sine theta, d theta, d phi. Now we will take all this information and then use them to find the potential outside the sphere. So to do that, we're going to pick a point outside the sphere. Now if you look at the sphere, and because the density is constant, is uniform, so rotating around the sphere wouldn't change anything. The sphere has something we call spherical symmetry. Spherical symmetry means there's no location better than another location outside the sphere. You cannot distinguish between locations. All locations seems symmetric or identical. So we can choose any point outside the sphere. We don't have to pick a specific point, but whatever point you take, you will always get the same answer. So to make things easy, I'm going to take that point to lie on the positive z-axis at a point called z0. So z0 is the location, is the coordinate of that point we are interested in. So we want to try to find the gravitational potential due to the mass, to the big mass shell, at the location z0. Now, if you concentrate on the small mass of the sphere, the red piece, now this is a point mass because it's so small, so you can think of it as a point mass. Now this point mass will create a gravitational potential at the point z0. From our discussion before, the small potential produced by this small mass is equal to, and that's I'm reading from the first line, it should equal to minus the constant g, times the small mass of that piece divided by the distance from the small mass, the red one, to the location z0. So that's the length of the blue vector. Now, what is the length of the blue vector? Remember, as we discussed before in the previous video, the blue vector is nothing but z0 vector minus r vector. And to find the length of this vector, we know that from our previous video that it's equal to the square root of z0 square plus r square minus 2 z0 times r times cosine the angle between the two vectors, which is nothing but the angle theta in spherical coordinates. So I'm going to put all that information back in the gravitational potential and try to calculate the total potential through integration on the surface of the shell. Now, because this is a shell, so we are integrating over the surface area. So putting everything there, the total gravitational potential should equal minus capital G. Now, sigma, we are assuming that sigma, that's the density, is constant, is uniform. So since it's a constant, I'm taking it out of the integration. And because the radius, we are integrating over the radius of the sphere, which is constant. So r squared is also outside the integration. And what is left is a double integral over the angle theta and the angle phi. So what is inside the integration is the numerator, sine theta d phi, and the denominator is simply the length of the blue vector. Now, for the limits, I only put the limits of the angle phi for a reason, just to note that if you look at the angle phi inside the integral, then you can see that it's a very easy integration. There is nothing in the denominator that depends on the angle phi. So the integration of phi is so simple, it's just 2 pi. So that's easy, done. And what is left is only the integration over theta. Now, if you look carefully at the denominator, you can see that z0 is just a constant, capital R is just a constant, so the only varying term in the denominator is cosine theta. So by integrating over phi, which is easily, then we have to integrate over the angle theta. But the integration for the angle theta is not difficult. You can just use substitution to do the integration. And here I'm writing the final answer for after integrating over theta. The answer is whatever constant here you have times this bracket. So that's the total gravitational potential due to the spherical shell. Now let's try to simplify this expression. And here we have to be very careful now. Are we talking about outside the shell? Or is Z0 outside the shell, or is it inside? Now in the picture, I put Z0 to be outside the shell, but even if I put it inside, I'm using the same method. So I'm gonna now find the answer for both cases, the outside and the inside cases. Now, something very, very important for students to notice is how do you simplify this expression in brackets? You have 2 square roots. Now, the first square root is easy to simplify. Remember that capital R is just constant, which is positive. Z0 is also positive. So the square root of the square of the sum of the both terms is nothing but just capital R plus Z0. And that's a positive quantity. Really, the trouble that some students will encounter is when simplifying the second term. That's the square root of capital R minus Z0 square. Now, when you simplify this, you cannot just take out the square root with the square. You have to be very careful because what you want to get is a positive quantity inside or coming out from this expression. So what is this second term? Well, that depends if you are inside the shell or if you are outside the shell. Now, if you are inside the shell, then capital R, that's the radius of the shell, is bigger than Z0. So R minus Z0 is the positive quantity, and that's the value of the square root. However, if you are outside the shell, then Z0 is the biggest. It is bigger than capital R, and so the square root is Z0 minus R, not the opposite. So be careful about this. Whenever you simplify a square root, you have to check that the answer is the absolute value of whatever inside. So here, there is a difference in the result between inside and outside, and that's what will make the result for inside and outside different. Now, the total mass of the whole spherical shell is nothing but sigma times the total surface area of a sphere, which is nothing but 4 pi times the radius square. So now, simplifying all that, we find the answer for outside the shell and for inside the shell. I will leave it to you to simplify these terms and to prove that. If you are outside the shell, the answer is nothing but minus capital G, the total mass of the shell, divided by Z0. And Z0, remember, it's the location of the point you are interested in to calculate the potential at. Now, because Z0 is just arbitrary point, and I can take it really anywhere, I'm not really obligated to take it on the Z-axis. Now I can remove this symbol Z0 and just put a general expression or a general symbol that's R outside. So the final answer, I will write it as the gravitational potential is minus G times the mass divided by small r. And what is that? That's exactly similar to the gravitational potential due to a point mass. So now we reached a very important conclusion, saying that if you have a spherical shell of uniform mass density and you are outside the shell, then the gravitational potential is exactly as if the shell was just a point mass located at the origin. That's a very interesting result. And based on that, the gravitational field strength, which is minus the gradient of the potential, is nothing but the famous, again, expression produced by a point mass located at the origin. So remember that. Now, what about inside the shell? Now, after simplification for inside the shell, you will find the result to be V is minus, again, capital G, mass of the shell, divided by, look what is there now, what is here? You get capital R. So that's the radius of the shell. But if you are inside the shell, and so the result saying that if you are inside the shell, then the potential is just a constant, which is equal to the potential at the surface. So no matter where you are inside the shell, the potential is constant. What does it mean now? This means that the field strength, which is the gradient of the constant, should be 0. So inside the spherical shell, the gravitational field is 0. There is no gravity. If you put anything, if you go inside the shell, you will not feel gravity. You only feel gravity if you are outside the shell. To finish this video, let's just make one remark. We proved this result based on an assumption, and the assumption was that density was uniform. So it means that the density does not depend on where you are on the surface. Now, if the density changes from location to a location on the surface, so let's say it's a function of theta and or function of the angle phi, then our conclusion will break down and it's not valid anymore. I'm not interested in this general case. The famous case of a uniform mass density is more famous and more important, and the conclusion is interesting. I will leave you with this, and I will see you in a different video.